Okay. Right. So we are relating. So we are let me quickly recall where we are. We still take a 5 minutes break at 10:45. Okay, I do apologize for this. So we came with deflection is equal to PL over AE, and that formula is familiar to most of you. Okay, some of you are not familiar with it. You see it now. So now we go into the elastic region. Okay, so what I've just drawn for you is a structure under axial loading, right? So when under axial loading with a certain load P, you have a new L1, and then we have a what? We have a deflection. Then from here, we look at our stress strain curve now. Okay, so we know that strain over here, right, is equal to L1 minus L0 divided by L0. Okay, well, stress over here, right, is equal, the stress over here is equal to P over A, right? So this expression over here, where epsilon equal to L1 minus L0 divided by L0, this is also equal to deflection divided by L0, okay, for that expression. And if you look at this line, okay, this straight line, this has a linear function, right? You have a linear function over here. And this linear function states that stress is equal to Young's modulus multiplied by epsilon. Okay, so over here, E over here is the Young's modulus, and this is the gradient. Epsilon is our variable, and stress is our response. So when you're doing your math course, I believe Sylvie taught you guys how to do functions, yes or no? So this is a very simple function. So now we write down, so stress is equal to E epsilon. Okay, so this is known as, so this, I believe this is our equation 3, and this is what we call our Hooke's law. Okay, so this is called, we address it as Hooke's law. Then we know that stress is equal to P over A, right? As seen in the graph down here, this is P over A. Young's modulus is still Young's modulus. Epsilon is equal to deflection over L0, right? Deflection over L0, right? So we have replaced some of the variables. Okay, so stress is equal to P over A, and then strain is equal to epsilon over, or deflection by L0. So therefore, once you rearrange this equation, you have P multiplied by L0 over AE. So this is our deflection. So you realize that this function and what I've written earlier over here, they're exactly what? They're exactly the same. So this is how we acquire the relationship, right? So I'm going to call this equation 4. So when is equation 4 valid? Okay, when is equation 4 valid? So when can we apply equation 4? Anyone?
Only when the...
Only in the elastic region.
Yeah.
Yep. Only in the elastic region. Well done. Why do you say that? Why do you say that only in elastic region? Anyone? Yeah, right. Why do you say that?
Because in the plastic region, you're deforming the piece.
No, no, that's not the case. It's only valid in elastic region due to equation number 3. Right? Equation number 3 said where stress is equal to E multiplied by what? Epsilon. Okay, so it's only applicable in the elastic region due to E multiplied by epsilon. What else? When is this equation valid? Anyone? I will zoom up for you so you can see better, so you can find the answer. Anyone? When is equation 4 valid? Linear. Good. Okay, so so equation 4 is only valid when stress and strain has a linear relationship. What else? What else? When is that equation valid? Strain is small. So i.e. we are still focused in the elastic region. What else? Jerome is writing something. Under axial loading condition only. Okay. Now, how do you know all this? Okay, so all these terms over here that you see down here, all right, all these terms down here that you see down here are known as the operating boundary. Okay, operating boundaries for equation number 4. Okay, for equation number 4. How you know all this? Because we derive it. Okay, we derive this expression. We derive equation number 4. How we derive? We draw what? We draw a stress strain curve, right? And we say that it's in the elastic region. And we draw this line that we realize that this is a what? Linear function. Yes or no? We drew all this, right? This is a linear function. The strain is small. That's obvious. It's because in the elastic region, strain are relatively small and only under axial loading. And this only under axial loading is because when we draw this diagram, it is only under what? Axial loading. Okay, so my advice is this: when you look at, don't be like me. Okay, when I was young, your age, I was really ignorant. Don't be like me. Okay, when you see an equation, sit down and see how the equation, or try to figure out, if you can have time, try to figure out how the equation is derived. And when you see how the equation is derived, okay, and sometimes it's as simple as by looking at a figure like this. Okay, that this is under what? Axial loading. Okay, you don't need to dig your brains out to figure that out. Okay, and then the strain is small. So by deriving, you come up with your operating boundaries. Okay, so now if we were to calculate deflection when the structure is under bending moment, equation 4 cannot be used anymore. I repeat again, if this is again, if the structure is under bending moment, this equation is not valid. This is only purely for under what? Under axial loading only. Okay, only, nothing else. Okay, now, so this is something relatively new. Some of you have seen it before. Some of you have seen it before. Now, let me talk about more about on the notation for elastic deformation. Okay, so let's look at the notation. Before I go on, anyone else, any question, please? Anyone?
What was the last boundary again?
Under axial loading condition only.
Okay, thanks.
Okay, and under bending is not going to be valid at all. Right. So the next thing we're going to look at the notation first. Then we're going to do an example. I think I've lectured enough already. Okay. If I keep on lecturing, no action, you guys will fall asleep. So let's look at the notation. Okay, for elastic deformation. So elastic deformation has two modes. Okay, so it can be either tensile or compression. Okay, it can be tensile, other compression. So if you look at tensile, if you have a structure, okay, and then your forces are pointing away from one another. Okay, so this is what we call tensile. Okay, tensile mode of stretching, right? So when it's tensile, what will happen is your deflection, okay, your stresses, your strain, they are all what? Positive. Okay, repeat, your deflection, your stresses, okay, your strain are all what? Positive. And the other mode that we see is compression. So the other mode that we have, right? This is compression. So in compression, deflection, stress, and strain, they are all what? Negative. Okay, they are all negative, right? So if you ask me in this today, what do you learn? Okay, this is method number 2. Method number 2 is fairly new, okay, to some of you, and this you have not seen this before. Okay, I'm going to go into example number 1 now. Okay, I'm going to go into example number 1 now. Okay, before I go into example number 1, any question, please? Okay, but remember, okay, this is for elastic deformation. Elastic deformation, positive is either tensile, negative is what? Compression. Okay, it's different from static analysis. Okay, anyone, any question before we look into static analysis? Anyone? No question. Okay, so if we just to recap, okay, if we were to use method number 1, usually employ static analysis. Okay, let me write on a different page. Okay, so method number 1, okay, usually apply static analysis. Okay, so what do I mean by static? Can you remember your static analysis? Yes or no? So what do I mean by static analysis? Anyone? So in static analysis, you have what? This is your X, and this is your Y, and this is your rotation about your what? Z-axis. Yes or no? right? So in static analysis, you're usually applied to summation about forces in the x direction, summation of forces